Hi, welcome to your lesson on modeling with trigonometric functions. Let's put trig functions into action by applying them to some real-world data. Let's begin here. Where are we? Do you have a guess? Okay, here's another picture from the same place. This place is known to be, I guess, the biggest city in the world with the largest variance in temperatures throughout the year. Here's another photo from there. Wow, this looks pretty cold. Oi, 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 look at that. That's quite cold. Here's where we are. Okay, right here, somewhere in Siberia. And here's the situation we're going to work on. Maria is planning an ecosystems trip to, and I have no idea how to pronounce that, but I'm going to say Verkhoyansk, a Russian town near the Arctic Circle, in order to study the permafrost. She knows that Verkhoyansk has a very cold climate and that the temperatures vary greatly. So we're going to take a look at that data now. Look at this. This is the temperature in that place taken at some point. That's pretty insane. Okay, the problem. To aid her planning, Maria wants to predict at what times in the year does the temperature change fastest. This has implications for the clothing she needs to pack, of course. And at what dates will the temperature be between -20 and -5 degrees Celsius? This has implications for the design of her experiments in the permafrost. Okay, here's the data she has. She found this on the internet. These are the months of the year: January, February, March, April, and so on, all the way to December. And here's the average temperature in that month in this town of Verkhoyansk. Look at those deep freeze temperatures here. Those are the averages for a month. That's quite cold. And even in the warmest months here, it only gets up to 15 degrees average. Okay, so she's going to develop a model. She graphed her data using technology, which we'll do in just a second as well, and she sees this shape to the data. She notices it resembles a sinusoidal function with a period of 12 months, because that's the data for 1 year. She then applies her knowledge that we've learned so far, and she's going to make a model. We're going to go through the process together as well. So again, here's the model she sees when she plots the data. It clearly has that shape of a sine or cosine wave. Okay, so let's begin there. But if we're going to make a model, let's remind ourselves of some things about sinusoidal functions that will help us with the model. So first of all, there's these two functions that take on this shape. They are the sine curve and they are the cosine curve. And both of these can be modified or transformed from their very basic shape to some other shape, like widened or made taller and so on, shifted a little bit by adding these numbers here called parameters. So we're going to work with those parameters and try to find the best model for the data we have. Don't forget, there are key things to consider: the principal axis, the amplitude, and the period. So here's a normal sine curve, and on this one we can see it has a center line, that midline, which is called the principal axis, right at y equals 0. And then from that midline it rises up 1 and it goes down 1. So its max point is 1 above, its minimum point is 1 below. Therefore we say the amplitude is 1. And then if we look at the length of one wave from beginning to end, that length is 360 degrees, and that's called the period, 360 degrees. Okay, that's a normal sine curve that has been unmodified, untransformed. Let's say we have this one, which has now parameters of 2, 3, and -1 here. How has it changed? Let's remind ourselves. First of all, the midline, or the principal axis, is now at y equals -1. The whole curve has shifted down 1, and that last parameter there tells us about the shifts of the curve. Now that we know where the midline is, we can then check this distance, and that's our amplitude. In this case, the amplitude is 2 units, and we can see the 2 in front here. So that number here tells us the amplitude. And finally, the number 3 here tells us more. So let's take a look. How long is one wave here? If you follow one wave, it completes in 120 degrees. And notice there are 1, 2, and 3 waves in 360. And that's what that number tells us. That number is called frequency. It tells us how many waves occur. So here we have a period of 120. So let's remind ourselves. The A parameter tells us the amplitude, the height of the wave, from midline to top or bottom. The D parameter, the one at the end, tells us about the vertical shift, how much the graph has moved up and down, and therefore where the location of the principal axis is. And the B parameter, the one inside there, that one, tells us the frequency. And if we take to find the period, how long it takes to complete one wave, we take 360 degrees, the normal period, and we divide by the frequency number we have there. So in this case, we got 120. Okay, great. Now that we've reminded ourselves of those properties, we can look at the data we have that Maria collected for this town in Russia, in Siberia. So first, let's begin as we always do. Let's kind of look at where the max is, and we know that's 15.5 because from our data that was the highest summer. Okay, what about the lower line? Where's the lower line at? Okay, if you remember, that highest or lowest winter temperature was -47 in January, so we put that line there. So now using our upper and lower, calculate where the principal axis is. Where's that middle line? Where's the middle between those two? Okay, before this we could kind of we could easily calculate in our head because the numbers were whole numbers and so on. Here we have this decimal and this negative number. So let's go back to the formula we had for calculating this, which is basically finding the average. We're looking for the average between these highs and lows. And to find an average, we always add the two data points. So we're adding 15.5 and -47 and divide by 2. That will give us the average. So that produces the midline, which is at -15.75. So that's pretty crazy to think about it that way. The average temperature in this city is -15.75. Yes, it does get above 0 here for several months, but on average throughout the year, it's that temperature. Midline, or the principal axis. Next, figure out the amplitude. So what's the height of the wave from the middle line to the top and to the bottom? It should be the same whether you look at it going up or going down. So what is it? Okay, to calculate that amplitude, we can just do upper temperature minus the midline, right? If we do this one minus this one, we'll get the difference between the two, which is the amplitude. There's two negatives here, it turns to a positive, so we can see the amplitude is 31.25. And that makes sense when you look at the data here. It takes about 30 degrees to get from -15 to +15 here, so 31.25. We could have done the same midline minus bottom temperature, this number minus this one, and we would have gotten the same number. So that's our amplitude. Okay, so now we can start looking at the model with the parameters. So far, we definitely know two of those numbers. So what would this model look like if you took the information we have so far and put it in? Okay, we would have this. Here's our amplitude in front, and here's that vertical shift right there. Okay, now let's concentrate on the B. Remember, the B tells you how many waves occur in 360 degrees. So see if you can calculate that. Well, we know the period is 12 months. This data goes for 12 months. And that's one full wave, right? Starts there, goes through the whole wave, and gets back to that point, and it will start again. So that's 12 months period. So we take 360 divided by 12, because we're saying how many of these waves will fit in 360. And if one wave takes only 12 months to complete, then we can do that. That tells us that there will be a frequency of 30. So 30 waves like this will complete in 360 degrees. Therefore, our frequency number here is 30. Great, there's our model. Let's go to Desmos and take a look at what that model looks like. Let's see if it's a good model for this data. So here I have put the data into Desmos. And here's the model. Oh, here's the midline first of all. Put that there. Okay, the principal axis. Here's the model we just created. I'm going to highlight it. Okay, take a look. Something's not right. It doesn't look like it's modeling it very well. So why? Let's take a look at that. This is some important stuff about trig functions that we should know. First of all, we've modeled with a sine curve. Okay, sine curve always begins at 0, but it begins at 0 at the center line, at the principal axis. So that's why that one begins there. Our model looks like it has the right height and everything and the right width. It just needs to be moved over, right? So something's not right. It's not in the right place. And we can see that there. Like if we draw the principal axis, I'm going to delete this again here. Here, where our model crosses the principal axis is away from the y-axis. There's a gap there. So that's why sine doesn't work. But if you remember, and I'm going to type it in here, a cosine model looks like this. Sorry, no, that's not big enough. That's not going to help. A cosine model also goes up and down, but a cosine model begins at the maximum point along the x-axis. I should, yeah, anyway, I'll click it here. So I took the same numbers and I made a cosine model. Check it out. It's better. It's better because notice, like I said, a cosine model, whereas sine, I'll put the sine on again, sine begins at the axis at 0 there. Cosine begins at the max point at the axis and then goes down. So Cosine seems to be better because we can see that our data reaches its max at the axis here. But in this case, it's the maximum negative value instead of that. So if we could take this blue one and just flip it over upside down, it would be better. It would be much better. So how do you flip something over? Well, first we just determined we need cosine because this begins at its maximum. And now we determined we have to flip that cosine. So to flip it, we always put a negative in front. So look at this negative here. Watch what happens. There, it flips over. So much better. So again, cosine is the best model instead of sine because we begin at one of the max values, or min, and then we flipped it over. It's pretty good. It's still a little bit off. And there's an easy fix for this. Very easy fix. And rather than fixing the curve, we can just change the data. When we began with January here, she called it 1 in her data. And notice that was 1. But what if all those data points just shifted over 1 unit to the left? Then our curve would be perfect. In other words, we want January not to be here, we want January to be right here. So why don't we make that 0? Watch this. 0. Great. Next one. So then February will be 1. And then 2, 3. I'm just changing the months over by 1 unit. 9, 10, 11. Okay, great. Hey, now our curve is great. Great cosine model, great sinusoidal model for our data. And now we know January is at 0 and December's at 11. Perfect. Looks like a very good model for our data. Great. Let's move forward with that model. Okay, so problem. These were the two questions that she wanted to answer. At what times of year does the temperature change fastest? And when is the temperature between -20 and -5? Let's take a look. So here's the model we just changed it to, cosine with the negative here. Here's our data, okay, and the model on there. And question A, when does the temperature change the fastest? So look at the graph. What about the graph tells you when something's changing faster rather than slower? Okay, I hope you're thinking it's the slope. When the graph has a steeper slope, that's when the temperatures are changing fastest. For example, here there's less slope, so temperatures are not changing as fast between January and February. But after that, here a little bit more, temperatures are changing quicker, and then here it seems to be they're changing the fastest. So right in this zone here, there's a steep slope, so the temperatures are changing quicker, and yes, they're going from negative to positive, so it's like spring is coming, temperatures are changing quicker, great. But it also happens on the other side of the curve. Here the temperatures don't change much between those 2 months and not much here, but over here again, there's that steepest slope going down, so that's when you're going from summer to fall and back to winter, the temperatures are going down much quicker, the average temperatures. So those months, if this is January, February, this is average March, so somewhere between March and May, in that zone. And again, this data is not perfect because we only have one data point for each month and it's an average for the month. So somewhere between March and May, we're seeing about 15 degrees up every month, right? It goes from -30 to -15, then to 0. So that's a quick change in temperatures. And that also happens September to November over here, where it's going down 15 degrees every month about. Okay, so that's kind of addressing her first problem. The second problem is, when is it between -20 and -5? So you can just put horizontal lines here, one at -20 or one at -5. And we're kind of in that same area, right? Roughly in those same months, March to May, maybe just March itself or April, I don't know. That's when the temperatures are between -20 and -5. And we cannot be precise here. That's important to note. And that's the final reflection. The data used here represents average monthly temperatures. Therefore, the predictions cannot be considered really precise. Like if you took that and tried to figure out exactly which month or what day of the month, that would not really be valid here because our data, again, is averages and only one data point per month. Okay, with that, I think you're ready to try one on your own. So here's a data table for tide, I guess for water measures in a harbor. See if you can plot that. You can use Desmos if you want as well. Plot that data, create a sinusoidal function that models it, just like the process we went through. And then answer C. The water needs to be 6 meters. So once you have that sine curve, you can figure out a horizontal line at 6 meters and figure out when Sam can take his boat into this harbor or not. So give this one a try. Give it a real try. Go through the process. It's really important that you try it. And let's see if you can get to the right answer. So here is the data. Here's part of the process. Here's a sinusoidal function. Notice that's cosine again because we began at a maximum point. We didn't begin at the midline, we began at the maximum point. So that always tells you you're going to use cosine. And then it follows the curve. There it is. And here's the answer for C. Check your work carefully. I hope you did okay with that. This is a great application of trigonometry in real life.